somewhat efficiently. And an interesting note here, so the way that these filters are usually done, whether they're done in the CodeCamera paper, you need to do computations over floats. There's no specification of floats in Lean yet, and even if we did define them there, we wouldn't want to compute with them sort of as Lean objects. So we can just expose a C++ float as a meta constant, along with some related operations, and use those instead. We're not proving anything about these. Again, they'll never show up in an actual proof, but we can use them to compute. So following the paper we will hear about tomorrow, following pretty much directly, we implement the same filters that they described. So we can have a k-nearest neighbors and a sparse Bayes classifier. I'm not going to walk through the code, just to show you that there is some. So this works. Downside, as you might expect, given this framework, we're working in a purely functional language that is really not optimized because this is a new language, and it's very much under development. It's not the fastest implementation that we could have in this. So it takes maybe 4 seconds to map over the environment, to build the data structures we need, a few more seconds to compute, to sort, etc. So we can produce a list of results in maybe 10 seconds, which isn't fast enough, but it works. The Lean libraries are still new, right? The system is under development, so we don't have as wide a collection of tools as we might in other languages. And it depends on this, I call it a hacked version of Lean, where we've added this float constant. That's not entirely necessary. There are ways around that, of course, but the easy implementation uses that. But on the other hand, this is very important. There's no need to compile anything. If you want to use this filter, you just import a Lean file that we can provide. So it's trivial installation. It basically becomes part of a Lean library, right? It's very easy to modify it. So if you want to change the notion of a feature, you want to add different kinds of features, say tagged attributes, it's very easy to sort of do those sorts of updates in line. Another interesting upside is that you can potentially verify parts of this. If you do parts of the process in core Lean instead of in meta Lean, you don't lose anything at evaluation time. It will evaluate exactly the same way as it does as a meta program, but it's done in core Lean, so you can prove facts about it in a sound way. What exactly you would want to verify about a relevance filter, I'm not entirely sure, but you could. Okay, so yeah, that's what I want to say about that part of this project. We're going to take a brief break and discuss computer algebra, and then we'll come back to relevance filtering. So computer algebra systems sort of offer a completely different array of tools than proof of systems do. They're complementary in some sense. Compute very quickly, we have huge libraries of functions available, they're easy to sit down and use, and they're very good for exploring mathematical theories, right? But at the same time, they're kind of useless for actually proving things. They're not particularly trustworthy, and they have no notion of justification built in. So at various points, people have connected computer algebra and proof of systems. We've done something similar for Lean. In effect, what we've provided is a generic translation procedure from Lean to Mathematica, from Mathematica to Lean. We have links in both directions. So Lean can call Mathematica, can query it for information. Mathematica can query Lean. And then we have some functions in each system that are supposed to take information from the other one and do what they are good at, what the other system is bad at. So Lean can request results from Mathematica and try to verify them. Mathematica can request information from Lean and try to display it, try to do what you want. Oh, and I should mention the work I'll talk about from now on is joint work with Mitch Awu, who's now at ANU. So the idea,